All right, guys. Today we are going to work on our last section, really, of the year. So congratulations, you've almost made it here to the end of Precalculus. So today we're going to talk about something called infinite limits. I'm trying to use some new technology here today when it comes to this PDF, so hopefully it works well for our video. So we've kind of talked so far about introduction to limits, how you can look at them on a graph, how you can look at them in a table, how you can evaluate some of them algebraically. Today we're going to talk about a specific type of limits called infinite limits, and I will post this blank PDF along on Google Classroom so you can fill things in if you want to print it out. But I'll be doing it here on the screen. So an infinite limit is limits as x approaches positive infinity or negative infinity. So really, in simple terms, it's the limit of a function as x values go way off to the left if we're talking about negative infinity, or to the right if we're talking about positive infinity. Okay, so in other words, if you're thinking about a coordinate plane, the limit as x approaches positive infinity is like, what are you seeing on the graph as we go way off in this direction? And then the limit as we approach negative infinity would be like, what are you seeing on the graph as you go way off in this direction? Okay. Now, there are some really, really simple rules that you can follow when you're doing these, but what I would like to do instead of just giving you the rules is allow us to kind of see them ourselves together as a class. So what we're going to do is I came up with 3 different functions here, and we're going to use a table for each one of these to find the limit as x approaches negative infinity and the limit as x approaches positive infinity for the function. Okay, now a really good way of thinking of as x approaches negative infinity is plug in a bunch of giant numbers that keep getting more and more negative or more and more positive, and see if you can come up with a trend for what's happening in the graph. Okay, so like if we're going to find the limit as x approaches negative infinity, we want to start by plugging in maybe a number that's pretty close to 0, and then a number that's further away from 0, and then a number that's even more further away from 0 in the negative direction, and then vice versa when we're going for the limit as x approaches positive infinity. And we'll look at the function values, and we'll see, does it look like it's approaching anything in particular? Okay. Now, a great way for us to do this is to use this table function on our calculator. So let's go ahead and we will examine this first one here. F of x equals x squared plus 2 divided by x cubed. So I'm going to go ahead and plug this in. X squared plus 2 divided by x cubed. Okay, and I mentioned this in our first section. If you are setting up your table, make sure you have it on ask, which means we're going to be able to actually plug in these x values ourselves. We'll go to second in table. I'm going to delete what I have from the last problem that we did together, and I'm going to go ahead and plug in these x values, okay, all these ones that are here in the chart. So I'm going to go negative 100, negative 10, negative 0.1, 0, 0.1, 10, and sorry about that, 10 and 100. Okay, and we're using the same values for all of these. So this will be the only time I have to plug in all these x values, but let's go ahead and let's see what's happening. So as we approach negative 100, we're at negative 0.01. Here we're at negative about 0.1. Here we're at about a negative 2010. There's an error when I try to plug in 0, which makes sense because if I try to plug in 0 here, I would divide by 0. And then we kind of get the exact same numbers on the other side, although they're positive instead of negative. Okay, so let's see if we can come up with an overall trend here. So the limit x approaches negative infinity for this function. So in this case, we're just looking at what's happening as our numbers are getting more negative. Well, think about it. As we're really close to 0, we are at a huge number. And then what we notice here is that huge number starts to get closer and closer to 0 as we become more and more negative, which gives us an indication that our limit as we approach negative infinity here is in fact 0. Okay. And then if we look in the positive direction, limit as we approach positive infinity for this function, we see a very similar trend. That would be what's happening as the numbers are getting larger. Well, we start with a huge y value, and our y value starts to get closer and closer to a value of 0. Okay. Now there is a pattern here, and when we're done, what I'd like us to do is see if we can identify that pattern. But for now, I'm just going to leave it at this particular function. The limit as we approach both negative infinity and positive infinity is equal to 0. Okay, as we start plugging in larger and larger and larger numbers into this function, whether they're large positive or negative numbers, we're going to start approaching a y value of 0. Okay. All right, let's look at our next function. Okay, we have f of x equals 2x squared plus 2x plus 1, all divided by x cubed. So I'm going to come over here and change this a little bit. Or, sorry, not divide cubed, but we're actually dividing by x squared. So 2x squared plus 2x plus 1 divided by x squared. Okay, and I'm going to go directly to my table here. Again, I'm using the same x values as the last time, so I'm just going to go ahead and pick these x, or just go ahead and write down these y values that I get. So 1.98, 1.81, 82. Once again, I see an error right here because I can't divide by 0. 122, 2.21, and 2.02. Okay, so let's see if we can come up with limits here for as we approach negative infinity and as we approach positive infinity for this particular function. Okay, so if we're approaching negative infinity, what we see is once again we start out with a big number, but as we're going this direction, this number is actually getting closer and closer and closer. It appears to a value of 2. Okay, looks like we're getting closer and closer to a value of 2. Okay, as we go further negative, we see here, and we could even try a really big negative number here just to be for sure. Let's try like 1,000 or 10,000. We'll try. Okay, look at how close that number is to 2. So as we plug in larger and larger negative numbers, it looks like we're approaching 2. Okay, and as we're approaching larger positive numbers, once again, it also looks like I'm getting closer to a value of 2. We start out really big, and then as we go along here, we start to get closer and closer to this value of 2. Oops, sorry. And if we wanted to, we could even plug in a really giant positive number, maybe 10,000 or something, and we see this number is super, super close to 2. Okay, so in this particular case, and again, there is a pattern here, as we approach both negative and positive infinity, we approach a y value of 2 on this function. All right. Okay, let's try one more function here with our charts. So this time we have negative x squared, okay, plus 2x plus 2, all divided by x. And let's take a look at our table. Okay, so negative 100 here. We've got 101 point, well, we'll say about 102-ish. Okay, here we have 11.8, negative 17.9, error 21.9, negative 7.8, negative 97.98. And I forgot to take this one off my chart, but what we can see here is if I plug in a huge positive number, this number continues to grow in the negative direction. Okay, so let's see if we can come up with some limits for this one. So we've got the limit as x approaches negative infinity and the limit as x approaches infinity of as positive infinity of f of x. Okay, all right, so let's look in the negative direction first. What we notice here is we start negative, we get a little bit larger, and then all of a sudden our number starts to grow huge. Okay, so like what it looks like happening here is my numbers get more and more negative, my y values start to get more and more positive at a huge, huge fast rate. And if I even tried to plug in something like negative, I don't know, let's try negative 100,000 here. Look at how large this number is. So what that looks like in our graph is like as x is going in this direction, my y value looks like it's shooting up to infinity. Okay. This is the first time we've seen this. The limit as x approaches negative infinity of this function is actually positive infinity. Okay. If we look on the other side, though, as we're approaching positive infinity for x, so in other words, as my x values are getting larger and larger and larger, look at what's happening to my numbers. Okay. Starts positive, it's getting more negative, and then all of a sudden it starts to get to a really big negative number. And if I plugged in something huge like 100,000, look at how large in the negative direction that this number gets. It looks like I'm shooting off to a value of negative infinity. Okay, so if we're starting to think about kind of what's happening in all these, each one of these functions was different, and we had a different scenario happening for the limits in all three of them. Okay, so what I'd like to do now is to kind of try to generalize this and see if there's a rule that we can follow every time that we do one of these problems. Okay, so let me do a little bit of vocabulary here. When you see this word degree, okay, what this word degree means is it's the highest exponent. Okay, the degree is the highest exponent. Okay, so let's go ahead and fill in some blanks here. So I'm going to say if the degree in the numerator is equal, or sorry, for this first one, let's say if the degree in the numerator is less than the degree in the denominator, then the limit as x approaches negative infinity and the limit as x approaches positive infinity is blank. Okay, well, what I'd like to do here is, do we have a scenario where the degree in the numerator is less than the degree in the denominator? Yes, we did. The very first example is one like this. The highest degree in the numerator here is squared. The highest degree in the denominator is cubed. And what we saw here was that the limit as we approach negative and positive infinity was 0. Okay. Now, a great question to ask ourselves is why? Okay. Why is the limit here 0? Okay. Well, a really easy way for me to show this is for us to look at a function like, let's see if I can get a smartboard up here. Okay, let's give this 1 second. Let's look at something like simple as maybe x divided by x plus 1 divided by x squared. Okay, let's say for example we were going to look at f of x equals x plus 1 divided by x squared. Okay, well notice this is a scenario where the degree in the numerator is less than the degree in the denominator. Okay, if I started trying to plug in numbers like let's do like 1, 5, and 10. Okay, if I plugged in 1 here, I'd get 1 plus 1, which is 2 divided by 1, so I would get 2. If I plugged in 5, I'd get 5 plus 1, 6 divided by 25. If I plug in 10, I get 10 plus 1 is 11 divided by 100. Notice what's happening to these numbers. 6/25, that's like what? That'll be about 0.24. And then 11 over 100 is like 0.11. Look at what's happening here to these values, okay? The numerator is growing at a much slower pace than the denominator. And what's going to happen to our fraction when we do this is that eventually the denominator is going to start to grow so fast compared to the numerator that it doesn't really matter what's up on the numerator. We're dividing by such a large number that my limit here is approaching 0. Okay, so in this scenario in which the degree in the numerator is less than the degree in the denominator, our denominator is growing so much faster that it makes my limit approach 0, whether I'm plugging in really large positive numbers or negative numbers. Okay, so that's our first scenario. Degree in the numerator is then the degree in the denominator. Okay, next scenario, if the degree in the numerator is, I'm going to put equal to the degree in the denominator, then let's think about what happens with our limit. Okay, we saw one scenario that was like this, and it came from this function here where the degree on the top was squared and the degree on the bottom was squared as well. Okay, well what happened here was when we approached negative infinity and positive infinity, we approached a y value of 2. Okay, it's important for us to understand where that number 2 is coming from. It comes from, I'm going to write this down and then we'll think about what it looks like on this problem. It comes from dividing the highest, we'll say dividing the coefficients of the highest powers. Okay, it comes from dividing the coefficients of the highest powers. And here's what I mean by that. Up on the top, the highest exponent was x squared and its coefficient was 2. And on the bottom, the highest exponent was squared and its coefficient was an invisible 1. When I divide 2 by 1, what I get is 2, and that is why the limit as we approach infinity in either direction is 2 for this function. Let's come up with a very basic example of this. Let's say we had y equals 2x plus 1 divided by 3x. Okay, and I wanted to know the limit. I'm going to try to plug in larger and larger values of x right here. Okay, all right, if I plug in 1, 2 plus 1 is 3, 3 times 1 is 3, so I would get 1. If I plug in 10, I would get 21 divided by 30. So that's about, that's 0.7. Okay. If I plug in 100, what I get here is 200 plus 1, which is 201, divided by 300. Okay. This is close to 2/3. Okay. Because 200 divided by 300 would be really close to 2/3. If I plugged in 1,000 here, I would get 2001 divided by 3,000. Okay. Now, what I want us to think about is, as we start plugging in larger and larger values of x, does this plus 1 really have that big of an effect on the change in my answer? The answer to that would be no, okay? This plus 1 has very little to do with anything that's happening in the function with larger and larger values. The only thing that I'm really concerned with at that point is what's going on between the coefficients of these functions, okay? Or the coefficients of these particular terms, all right? Once I get to values as large as 1,000, that plus 1 is so negligible because 2001 divided by 3,000 is so close to just 2,000 divided by 3,000. Okay, and that's why as I start plugging in larger and larger numbers, my limit approaches just 2/3. Okay, and that's why the limit for this function that we saw on this problem just became 2, because eventually as I was plugging in larger and larger numbers, this 2x plus 1 that's happening over here is not really going to have that much of an effect on my answer. I'm only concerned with what's going on with these coefficients of the highest power. This 2 divided by 1 gives me this limit of 2. Okay. All right, last scenario here is if the degree in the numerator is greater than the degree in the denominator, then the limit as x approaches infinity and the limit as x approaches negative infinity is either going to be positive infinity or negative infinity, depending on the signs of the function. Okay, and I'm going to leave that as it is right now. We'll get to an example on the back that we'll see in just a moment. But we did see this scenario happening right here in our third example, in which the highest power on top was squared, the highest power on the bottom was 1. So this numerator is greater than the denominator. And we saw that when we calculated these limits, we got positive infinity in one direction and we got negative infinity in the other direction. I'll explain where that comes from with the signs in just a second, but one thing that I want us to think about, let's say we had x cubed divided by x plus 1. Okay, well, once again, let's try and plug in some bigger numbers here. If I plug in 1, 1 plus 1, or sorry, I get 1/2. If I plug in 10, 10 cubed is, let's see, 10 cubed is 1,000. And then 10 plus 1 is 11. Okay, so this is a pretty big number. And then if I plug in 100, 100 cubed is like, what's that, 6 zeros? That'd be like a million divided by just 101. If I divide a million by 100, I get a really big number when I'm done. So what we see here is that the larger and larger values that we plug in for x, we start to approach positive infinity. Okay, as I plug in larger and larger values of x, the numerator is only going to continue to keep growing so much faster than the denominator, which causes my overall fraction to approach infinity. Okay. Now I know we're taking a long time on this front side. This is actually the longest conceptual part of today, which is why I'm spending so much time on it. A great question that you can ask yourself anytime you're trying to evaluate these limits as we approach infinity is to ask, which is growing faster, the top or the bottom? Okay, if you can identify which one's growing faster, it makes it a lot easier to conceptualize what's happening with the limit. And the idea of which one's growing faster has everything to do with which one has the larger exponent. If the top has a smaller exponent than the bottom, it means the bottom's growing faster. If the bottom's growing faster, it means we have to be approaching a value of 0. Okay, if the exponents on the top and bottom are the same, that means they're growing at the same rate. The only thing that's going to affect our answer is the coefficients in front of the terms that have the highest exponents. Okay, if the top has a higher exponent than the bottom, which is like what happened here, then that means the top is growing much faster. If the top is growing much faster, that makes us approach either positive or negative infinity. It just depends on what the signs are, which we'll see as we get to a couple of these problems on the back. Okay, so let's start out here with example number 1, or we'll go through all of these together. So we've got the limit as x approaches infinity of 3x squared divided by 2x squared minus 1. Both of these have the same degree on top and bottom, which means they're growing at the same rate. The only thing that's going to affect our answer is these coefficients in the front. Okay, in this case, the top is a 3, the bottom is a 2, so when I divide them, I get 3 halves. Okay, so I'll say for each of these, I'll say whether they're growing at, or what kind of rate they're growing at. Okay, all right, in this case, limit as x approaches negative infinity of 5x to the 7th divided by 3x to the 11th plus 5. In this case, the bottom grows faster. And the reason why the bottom grows faster is because the exponent on the bottom is much larger than the exponent on top. Okay, if the bottom's growing faster, that means the bottom's getting larger than the top at a much faster rate, which eventually makes my fraction approach 0 for my answer, just like we saw on this first problem here, in which we had an x squared on top and an x cubed on the bottom. Okay. All right, next one, limit as x approaches infinity of 5x cubed divided by 4x squared plus 3. In this case, the top grows faster because it has a higher exponent. So here's what I'm talking about when I say think about the signs. Okay, you need to think about what happens as I plug in really large numbers. What happens to my signs? Okay, in this case, I'm approaching positive infinity. 5 times a humongous number cubed. Well, if that number is positive, I'm going to have a positive big number on top. And then on the bottom, 4 times any number squared in the world is positive. So 4 times a positive number gives me a positive, plus 3 also gives me a positive. A positive divided by, and I shouldn't even really write infinity here. I should just write positive and negative because that's what I'm trying to be concerned with. Positive divided by positive, it leaves me with positive infinity. Okay, so I know my answer has to be positive or negative infinity since the top is growing faster. In this case, the way the signs work out, a positive divided by a positive yields a positive answer. Okay. If we try this next one, the limit as x approaches negative infinity of negative 6x cubed plus 5. Well, what that is an invisible 1 on the bottom. This 1 is not changing at all. So once again, the top is growing faster here, which means my answer, you got a 50-50 shot. It's either going to be positive infinity or negative infinity. If we try this one again, think through what we're seeing right here. Sorry, give me one moment. Thinking about what we're seeing right here. What I'm left with is negative, and then 6 times, if I take a negative number and I cube it, a negative number cubed is a negative number, and then we're adding 5. So we're cubing infinity, which gives us a massive negative number, but we're multiplying it by this negative in front. So a negative times a negative gives me a positive. And then if all I'm going to do is add 5 to that, well, it's even going to get more positive. So I have a humongous positive number plus 5, which yields an answer of positive infinity. Okay. Now, if, for example, this had not been a negative 6, and instead it had been a positive 6, for example, then we would have had a positive times a negative number, which would have given me a negative infinity plus 5, which is negligible for taking a large negative number and adding 5. So then my answer would have been negative infinity instead of positive infinity. So that's what I'm talking about when I say that the signs matter. Think about what you would get if you plugged in really large negative or really large positive numbers, depending on what the answers, or depending on what the question's asking, and that will help you get to your final answer of either positive or negative in any scenario in which the top is growing faster. Okay. All right, a couple other little things here to finish out. Want us to do a little bit of visualization real quick with this. So let's think about this problem. The limit as x approaches infinity of, I'm actually done with the calculator, so I'm going to make this a little bit larger for us, if possible. I don't know if it'll work or not. Limit as x approaches infinity of 5x divided by x plus 2. Okay. In this case, top and bottom are growing at the same pace because the highest exponent for both of them is 1, so I need to divide the coefficients. 5 divided by 1 gives me 5. Okay, so my guess is that as we approach way to the right and way to the left, we approach a y value of 5. And in fact, when we graph this, this is what we see. Okay, as we go way to the right, as we go way to the left, my graph is approaching this y value of 5. It doesn't quite touch it, but it gets really close. If you guys remember from graphing, that line that we get really, really close to but don't touch is called an asymptote. And in this case, this is a horizontal asymptote. Okay, so one way of thinking about the limit as we approach positive or negative infinity is thinking about the horizontal asymptote of the function. So for example, like in this function right here, 3x squared divided by 2x squared minus 1, if you were going to graph this, what you would see is that as we approach positive or negative infinity, if you had a horizontal line at, if this was 2 and this was 1, 3 halves would be halfway in between. You would see that the graph approaches that horizontal line of y equals 3 halves as it goes way off to the right and way off to the left. This one would approach a y value of 0. This function, remember, it could be either positive or negative infinity. If we're increasing in the positive direction, what we would see is our graph, as you go way off this way, your graph would be shooting up to positive infinity. Okay, this one as well would be shooting up to positive infinity as we go way off to, as we approach, in this case, negative infinity, our graph would be shooting way off to positive infinity. Okay. So that's what some of this, another way of thinking about these is, it's really just asking what's happening way as we go way to the left and way to the right. If it's approaching a finite number, like 0 or something where you can divide the coefficients, then what that would look like is just a horizontal asymptote. Okay. All right, a couple more examples here. Couple special cases. I won't ask too much about these, but I might mention them, so it's important to know them. Let's say that we were looking at this. The limit is x approaching infinity of the square root of 4x cubed plus 7x divided by 16x cubed minus 3. Okay. Now, this is a little bit different because we have a square root here and we haven't seen a square root in any of these other problems. But if you remember what I was talking about earlier, if you are doing something like 10 plus 1 over, sorry, let's think about it like this. Let's say you had x plus 1 over x. If you were thinking about this as 1 plus 1 over 1, and then 10 plus 1 over 10, and then 100 plus 1 over 100, and then 1,000 plus 1 over 1,000. Eventually, we get to the point where this plus 1 doesn't really matter anymore, okay? And that's why if you were going to find the limit as x approaches infinity of this function, you would just get 1 divided by 1, which is 1, because eventually we get to the point where that plus 1 is so negligible it doesn't have much of an effect on the function. The same thing happens on the limit if I plug in values of x that are getting larger and larger. The only thing that ends up mattering is not this stuff, but the stuff that's going on right here, okay? So a way of thinking about this is that this function right here is approximately the same thing if we're calculating a limit as x approaches infinity. This is approximately the same thing as just 4x cubed divided by 16x cubed. Because as we plug in larger and larger values, you can almost ignore this stuff at the end. And if we keep approximating this more and more, these x cubes cancel. 4 divided by 16 simplifies down to 1/4. And the square root of 1/4 is 1/2. So this function, as we approach infinity, is going to eventually approach a y value of 1/2. Okay. One other example here to close this out, very similar to the last one. If we're approaching a value of negative infinity, okay, if we're approaching a value of negative infinity, let's think about what would happen in this particular function. Okay. It looks as if the top power is smaller than the bottom power. Okay? Which would, at first glance, you'd think that maybe the limit as we approach negative infinity here would be 0, but we have to remember that there is a square root happening on the bottom of this function. As we plug in larger and larger values, as we mentioned before, anything that has smaller powers starts to almost not matter anymore. Okay? So in this case, I'm going to go ahead and let's say we kind of, since we're approaching positive or negative infinity, let's kind of try to, again, we're approximately, not the exact same, but this is almost the exact same thing as us only having this. Okay? And then if we do a little bit more math with all of this, okay, the square root of 9x to the fourth is 3x squared. And I can now kind of say, well, those x squareds divide out, which means that my limit here is just 2/3. Okay, so if you see problems that involve square roots, think about what would happen maybe if you ignored what was underneath the square root other than just the highest power. That's a good way of helping us find any limits on problems that look like that. Okay, hopefully this was decently helpful and you kind of understand. The biggest thing that I can describe when you're trying to find limits as they go way off to the left and way off to the right is to ask this question: which is growing faster, the top or the bottom? Okay, which grows faster, top or bottom? Okay, if you can conceptualize that question right there, you will never be able to, or you will never not be able to evaluate one of these just by kind of thinking about it. Okay, there are rules that you can memorize. Okay, but it is good to know what's going on with those rules and where they come from if we want to have an understanding of what we see when we're looking at a graph. Okay. All right, guys, that'll conclude our videos for the year. So congratulations for getting to the end of Precalculus. I'll put an assignment up that goes along with this, and we should have one final to close out the year. I'll talk to y'all later. Bye.